Okay, now we will move on to operator for momentum. So let us begin with expectation of operator P. Actually, as usual, like what we have done for position operator, we begin with the position space wave function, and that is written in terms of momentum space wave function using the Fourier analysis. Okay, so we have psi of x comma t, operator P psi dx. Yes, as usual, we represent or we sandwich P between psi star and psi. Okay, now let us give the values. We have given the values. The constant 1 by square root of 2 pi h cut 2 times 1 by square root of 2 pi h cut from psi star and psi. So we have 1 by 2 pi h cut integral dx and integral phi star and e raised to minus ipx by h cut dp from psi star. So we have that. Then for P in position representation, what we have is minus I h cut dou by dou x. Then values of psi is integral phi of P prime comma t, just to make P a variable, e raised to I P prime x by h cut dp prime. Now let us think about this operation, dou by dou x of this one. So let us take minus I h cut outside, that's a constant, and do the operation dou by dou x of this one. As you can see, this is independent of dou by dou x, so let us keep it outside and differentiate exponential part. So we have constant term I p prime by h cut is a constant, so that into dou x by dou x. So exponential this one I p prime x by h cut into differentiating this one I p prime by h cut into dou x by dou x. So we have this one as a constant. Okay, now let us collect as we have been doing. The first step is to integrate the x part and obtain the Dirac delta function. For that integrating, we have taken 2 pi also inside, 1 by 2 pi into 1 by 2 pi along with exponential part and integral over dx. So what we get is h cut into Dirac delta function. And next we perform P prime integral. So we take phi of P prime comma t into P prime as the function here. So yeah, let this get cancelled. So this is a function part and this is the Dirac delta function. So using the property of Dirac delta function, we can have the function which was actually in terms of P prime. The integral is over dp prime, actually turns out to be with the variable p. So we have p into phi of p comma t. See, now we have almost reached the completed the derivation. So now we have, as you can see, it is from minus infinity to plus infinity, phi star p comma t p phi of pt dp. What does it mean? This is the actually p is sandwiched between the wave function psi star and psi, like phi star and phi. So we can say that it is the expectation value of operator p. That can also be written like this, mod phi of p square into p dp. That is actually the expectation value of momentum operator in momentum space. Okay, now we move on to equation of motion in momentum space. For that, let us begin with equation 3.117, which indicates the momentum space wave function using Fourier analysis. Okay, we begin with that. Phi of p comma t is equal to 1 by square root of 2 pi h cut integral psi of x comma t e raised to minus I p x by h cut dx. Now we are going to multiply I h cut on both the sides and differentiate it with dou by dou t. Here we have I h cut dou by dou t of phi of p comma t, which is equal to constant into integral I h cut dou by dou t on this side also. Here we have the only function of t is psi, so let us confine ourselves with differentiating only psi with respect to t. This is independent of time. Okay. Now we can replace this term I h cut dou by dou t with our Hamiltonian operator minus h cut square by 2m del square or dou square psi by dou square by dou x square plus v. So I have given the value here 1 by 2 pi square root of 2 pi h cut into integral the value of I h cut dou by dou t is given here, then psi e raised to minus I p x by h cut dx. Now what we are going to do is I am going to separate these two into two equations, two integrals. First integral involves minus h cut square by 2m dou square by dou x square only. The second term includes v of x into psi. Now I have taken the first term and let us integrate it. So yeah, my first function is exponential and second function is dou square psi by dou x square. Okay, let us integrate it. First function into integral of the second means one order of differentiation will be reduced because of the cancellation of differentiation and integration. So I have dou psi by dou x and apply the limit between minus infinity to plus infinity. Again, so when once we have either psi or dou psi by dou x between the limit minus infinity to plus infinity, we can use the condition of finiteness of wave function. That means either the variable x tends to plus or minus infinity, our wave function will be reduced to 0. So we are using that condition, so this term will be cancelled. First term will be 0 when we apply limits. Now we have the second term. Okay, let us rewrite it. Minus of minus plus, so I have I by h cut p integral e raised to minus I p x by h cut dou psi by dou x dx. Again integrate it. Okay, p also comes like a constant, so let it be outside. So again first function is e raised to minus I p x by h cut into integral of the second is psi. Apply the limits minus infinity to plus infinity minus of integral of derivative of first again. So minus I p by h cut into e raised to minus I p x by h cut into integral of the second psi dx. Again this one cancels applying the same condition because of the psi here, so this also cancel out. So what remains is e raised to integral e raised to minus I p x by h cut dou square psi by dou x square dx is equal to, we have 2 ip, so minus I square is minus 1, so plus p square by h cut square, then integral e raised to minus ipx by h cut psi dx. Now let us move on with the integral second one, v of x psi of x comma t e raised to minus ipx by h cut dx. Okay, now after integrating the first term we have this is our equation, and after integrating the first equation we have this one and the second term. Now what we are going to do is we are going to apply the value of a psi. Again, using the Fourier analysis, we have 1 by square root of 2 pi h cut integral phi of p comma t e raised to ipx by h cut dp. But when we substitute the value of this one, we already have a p in the equation, so we are going to make it a variable, so we shall give it as p prime. Okay, we have substituted it. Now we will take each term. Now you have to note that we already have an integral over dx here in both the terms, and additional to that we have an integration over dp prime when we apply the value of a psi of x comma t. So let us take the first term, term 1. So like the previous integrations we have done, let us integrate over dx first. For that, exponential part is collected together, and 1 by 2 pi e raised to I p prime minus p x by h cut dx turns out to be the Dirac delta function. So h cut cancels. Now what remains is p square by 2m phi of p prime comma t dp prime. Once more integrate over dp prime, that is using the property of Dirac delta function. So we can have phi of p comma t into p square by 2m. I think it's clear. We have done this type of integration now twice for finding the position operator in momentum space as well as momentum operator in momentum space. So now we are familiar with this integration where we obtain Dirac delta function, and using the Dirac delta function how we obtain the function substituted with the variable p. So performing both the integration, we have p square by 2m phi of p comma t. Now similar way we have to evaluate the second term as well. For the second term also we have to use the same way of integration, that is term 2